Hi, everyone. So in my talk, I'm going to speak a bit about some of my early experience in deep learning and how that work took me to doing from sort of my origins, doing work in healthcare, towards related problems in finance, or at least related from a sort of shape of the data standpoint. And then ultimately, what I'd like to concentrate the second half of the talk on is sort of things that I think are missing, or fundamental obstacles to sort of using deep learning in a broader set of I think sort of important contexts, and specifically that will be the dealing with the fact that distribution shift exists, and that we're not just training on historical data and also evaluating on historical data. So by reference, my name is Zachary Lipton. I run a lab at CMU where I'm co-appointed, both in the machine learning department and the Tepper School of Business and the operations research group. I've got a nice eclectic lab. We have a lot of students from machine learning, some from language technology, some from Tepper, some from statistics. I actually have a postdoc in philosophy right now. And we look at a wide range of problems, but our sort of overarching theme is machine learning that's applicable in the real world. So we care about kind of crucial real world tasks like healthcare and economic kind of settings. We care about things like causality or robustness that are sort of, and also sort of social impact and ethical concerns of AI algorithms that are sort of we see as being the sort of conceptual barriers to broader application of this technology. And so I'll discuss work. I have an irresponsible number of slides relative to the number of minutes that I have, but I'm going to try to get through it. We'll see how good a job I do. I'm just going to leave this up here for reference. These are a bunch of the papers that we'll be discussing. Actually, the Failing Loudly paper was published at NeurIPS last year, but I've apparently failed to update its entry in the outline slide. So overall, I think it's sort of fair to look at like one sort of lens of looking at what's happening in machine learning is sort of a progression from simple prediction. So, a handful of tools that are, relatively simple to describe, amenable to analysis, kind of standard tools of statisticians and sort of early machine learners, and making some very strong assumptions about, how well-behaved and neatly processed the data is, to the world that deep learning has opened up, which is the world of fancy prediction. And by fancy prediction, I mean we're still doing qualitatively the same kind of learning. We're still doing empirical risk minimization. We're still hoping for generalization to unseen data from the same distribution. But deep learning has afforded us this ability to look at all kinds of modalities of data that we couldn't deal with before. Things like sensory data, images, natural language, to mine patterns that are highly nonlinear and that maybe even are sort of barely evident in the raw representation and really require some kind of sophisticated processing of the data in order to some kind of hierarchical structure to get from the raw features all the way up to the sorts of things that we'd want to be able to predict. And we're getting better at that, and we continue to get better at that. But I guess the thing that I'm sort of most interested in these days is what's next beyond i.i.d. prediction? Even assuming that this the train's left the station and we're going to keep getting better and better at doing prediction. What about all the problems that we're going out there and trying to apply this technology on that really aren't at their core prediction problems? There's really some other dimension to it. Either we're making decisions and this requires causal insights, or we're making predictions, but we're making predictions in a world that's changing and for which historical data isn't perfectly representative. Sort of what principles allow us to operate effectively in these sort of more realistic type scenarios that require intelligent behavior. So I can give a little walk through this timeline in the context of healthcare, right? So when I entered the field around 2012, 2013, I guess 2012 when I was first getting interested in it, and 2013 when I began my PhD, deep learning, like the first breakthrough results had just happened, but they hadn't really permeated through the wider areas of application of machine learning yet. And I kind of caught the tail end of like a classic world of machine learning for healthcare, which still might even be arguably the if not the most hyped area, still the lion's share of work, which is mostly tabular data, so sort of data you could find in a spreadsheet, fixed length data, so each individual patient, say, represented by a fixed set of numerical values, traditional classification and regression problems, maybe a little bit of survival modeling, stuff like that. And the recipe was, go out, get some data, choose something, call it the target, select some of your features, call them the covariates or the features, and compare a bunch of off-the-shelf algorithms and see, how well they perform. And so what deep learning has done here is it's given us flexible models capable of handling high-dimensional data, capable of dealing with sensory and spatial data, capable of dealing with long and varying length time series. So this is necessary because some patients maybe have only been in the ICU for 12 hours, and some have been there for 12 days, and some have been there for 12 weeks. And we want to have a single model that's able to leverage data from each of these patients to make better predictions for the others. So handling varying length time series is useful. They give us, at least if all we care about is prediction, they give us kind of simple ways of dealing effectively with missing data. This is different from the way that data is missing in the context of, say, causality or potential outcomes. I'm specifically speaking about missing covariates. I think the others remain kind of confounding problems. And indeed, there have been some breakthrough successes. So, for example, in diagnosing diabetic retinopathy, you might have seen in stories that deep algorithms perform as well or better than humans. These claims always need to be very carefully qualified because you say humans as evaluated how, and it's humans versus machines when both are evaluated on, say, i.i.d. holdout data drawn from a random partition of the same data that was used to train the model. So you haven't seen the same examples, but they sort of share a statistical character, and we're not allowing that equipment has changed between when the model was trained and when it's deployed. That's the sort of thing we do need to worry about in reality, though. Again, dermatologist level classification of skin cancer was another kind of grabby headline, and it is very exciting result. At the same time, it's limited to this assumption that you're evaluating the model under the most favorable of circumstances. If you change the distribution, as we'll get to, things can change and break in all kinds of ways. And certainly you have quite a lot of hype here and quite a lot of excitement, but maybe I'd argue some of it a little bit premature. So here's an article by some leading folks in the medical informatics world, and they're asking this question: are we on the precipice of solving medicine? And they have a call for, or maybe those are my words, my sort of maybe unfavorable interpretation. But their article is basically a call for deep learning healthcare, and they specifically say that now is the time to create smarter healthcare systems in which the best treatment decisions are computationally learned. This is interesting because it raises the question of, well, what do we mean decisions? We were never talking about decisions in the first place. Almost all this technology was developed to make better predictions. So decisions, we have to not just know what is the decision that was likely to be made historically, but how would the outcome be different if we were to intervene and make a different decision? Can we make better decisions? Ultimately, we're concerned with making smarter decisions. This speaks to some desiderata that's not totally captured within the predictive paradigm. So this sort of and these questions are actually, hopefully my talk will give you a little bit of a flavor of how they're all quite a bit related to each other, causality and distribution shift. But, speak to the kinds of flavor that, we get excited about in the lab as we start seeing these areas where the technology is being applied, where there's some kind of fundamental mismatch between the problem people want to address and the ones that the current machinery seems to be addressing. So I can, sort of walk through a little example of early healthcare project that I worked on, and kind of just give a feel for why we think the deep learning is exciting and then the predictive tools are exciting. So this was work in 2016. So recurrent neural networks, which have been around since, I guess, talked about since the 80s and 90s, but which really were gotten to work in an impressive way in maybe around 2009, 2010, when only a couple people knew about it. This is like the work of Alex Graves on handwriting recognition and handwriting generation. And in 2011, 2012, Ilya Sutskever and others started using them for language modeling, and they became popular in natural language processing, especially with the breakthrough of sort of sequence-to-sequence learning in 2014. So it was around maybe 2015 that the rest of the world really started waking up and started using recurrent neural networks. At the time, it was hard to find sort of anyone who had experience training them, at least at my university, for example. So I got interested in looking at this data or looking at these models and seeing the success that recurrent neural networks have, and wondering could we sort of get these sorts of gains, get these kinds of impressive performance on medical data and not just say on sequences that arise in say natural language. So we had some partners over here. So this is a collaboration with David Kale over on the left, my advisor, Charles Elkin over on the right, and in the center is Randall Wetzel. And anyone who's worked on healthcare knows that the most important person in the project is the person who can make it possible for you to get data. So in that sense, Randall was the most important person in the project. He's a physician who runs the Pediatric Intensive Care Unit at Children's Hospital LA, and has been a sort of big, long-time supporter of machine learning research efforts. And so the data that we got access to had 10,000 patients. These were basically 13 variables, each sort of a irregularly sampled time series of sensor data or lab tests or some frequently coded information. We had 120 labels that we were trying to predict. So the premise was just to say, let's look at this sort of frequently recorded data, the frequently evolving data, and see, can we infer from that, can we do the task of phenotyping, essentially? It's maybe a more accurate term than diagnosis, which is, can we recognize which diagnoses apply to each of these patients just by tracking these frequently observed data? And the complications, again, are irregular sampling, misleading values, varying length sequences. So you can see over here, part of the challenge is we have data that looks like this. If we try to turn this into some kind of wall clock windowing, we have some data is sort of missing in a particular window. It's not that the data is missing, but it's more like it's missing as an artifact of the resampling. So that measurement was never observed inside that window. You have other features that maybe were never observed at all to that point. You have other features that were observed exactly once, so that's easy. Maybe we just keep that value. You have other things that are observed multiple times. And ultimately, a recurrent neural network is expecting something a little bit more like what we see on the bottom, which is even if the data isn't fixed length, it consists of a sequence where each time step is represented by a fixed length representation of the observation. And one kind of tricky thing with recurrent neural networks here is you have some sort of seemingly arbitrary design choices. It's not immediately obvious that you should solve this by windowing things into hours. Even if you decided you were going to do a wall clock windowing, why hours? Why not every 2 hours? Why not every 6 hours? Why not every day? We ultimately chose this because we wanted to be sort of as high resolution as possible while being within the sort of within the range where we knew that we were inside the lengths of data that the recurrent neural networks at the time could tolerate without having sort of learning instability. So we were sort of playing off over here that we knew that there was certain things were updated fairly frequently. So we knew how frequently our most frequently updated features were on average, and we wanted to be have our window somewhat close to that length. But we also knew that the shorter we made our window, the longer each patient's sort of history became in terms of as measured in number of time steps. So that gave us a range of feasibility to play with. Note that in the most extreme case, one thing you could do is you could not window to the wall clock at all, but you could rather feed in every single measurement as its own time step. So it's really just a sequence of measurements, and then maybe one of your features could be something like, what was the time delta, from the last measurement to this measurement. You could think of that as being sort of analogous to the doctor reading through the file temporally. So if one day had a lot of activity, they spend more time on that. They're all sort of intuitive, and these kinds of questions in deep learning, one interesting thing about deep learning is that theory doesn't always give you really clear guidance about what is the right thing to do. So in our case, these sort of aren't, we consider these things to be empirical questions, and we ultimately tried all of these options and settled on what seemed to give us by far the best performance. So we engaged in some kind of heuristic preprocessing. When there were multiple values inside a window, we averaged them. When there was one value, we just kept it. When a value was missing entirely, in that time sequence, we forward filled from the last time it was observed. And when it was really missing entirely, like it wasn't even available earlier in that sequence, we imputed a clinically normal value. And that was a kind of arbitrary decision. And that actually, I think, is something we weren't too satisfied with, because the value being missing might actually mean it's very likely to be normal, and that's why they didn't measure it. Or it might mean that it was sort of already known to be abnormal from, maybe some previous visit or something, and so it wasn't worth testing. One thing that we did next is we explored ways of incorporating for our predictive model features that indicated whether each observation was actually real or imputed. So we added these indicators. We came up with a few different ways of doing this. One is that you could do the imputation plus the indicators. The other is you could just zero fill but give the indicators. It turned out that zero filling with indicators performs slightly better. So imputation performs better than no imputation, I think, but no imputation with indicators performs better than no imputation or than imputation with indicators. So we augmented our model in this way, where each time you saw basically a sequence, each time you saw the numerical values corresponding to the time step with zero filling, plus you also got for each feature a surrogate feature, which just was like an indicator, yes or no, was this a real observation, or was this a time step in which there was no observation, in which there was missing data. It turns out this is pretty powerful, and even though if you do this kind of missing value indicator for a linear model, it could just learn a replacement value, but for an RNN it could learn sort of arbitrary sort of imputation schemes implicitly. So we're approaching the problem of multi-label diagnosis. It's multi-label classification. Each patient is associated with some subset of the diagnoses, but they're not necessarily mutually exclusive. So someone, unfortunately, like in this case, could have both diabetes and a brain tumor. It's unfortunate but possible. In fact, in our data set, I think the average patient has something like 2 diagnoses associated with them. So our output's a sigmoid unit on every output unit. Our objective is to maximize the likelihood of all the labels. We compare against traditional baselines. And here's another key thing in the application of deep learning, where I think a lot of people are getting confused these days, is that a lot of times you see results tables where people compare head-to-head, logistic regression, random forest, and deep learning, all applied on the raw features. The problem here is this isn't really a fair comparison, because this isn't how anyone applies a linear model, right? So the standard practice for applying linear models is that you hand engineer a bunch of features using all of your sort of prior knowledge, and then you feed this into a model where you just have a linear classifier on top. Whereas with the MLP, instead of handcrafting the features, you're learning the features from relatively raw data. So to compare an MLP against a logistic regression when both are compared on the raw features is not quite fair. And so one thing that we did here, and that we try to do in all of our work, is when possible to really give an edge to the baselines by doing what a real practitioner in the weeds would actually do, which is adding all these expertly handcrafted features. Like they know that what's really important here is, say, like the slope of the trajectory of the feature over time or something like that. So we make that a feature. We had a multi-label, an MLP. We use dropout regularization, all the bells and whistles that were common at the time. For RNNs, the sort of standard thing to do would just be to apply the loss on the very final time step, if that was all we cared about. So just feed in all the data, get out your prediction, and compare it to the truth. One thing that we did that turned out to be effective, even if all we cared about was the performance on the final time step, was something that we call target replication. So we just try to predict the target, even if the target is perhaps, we only actually care about how the model performs when predicting the target after seeing all of the data. We actually have the model make a prediction at every single time step, compare it to the real label, and backpropagate through the loss as applied on every time step. And we just have a hyperparameter that tunes between how much do we care about the loss at the very last time step and the average of the losses over all the time steps. So you could think about this as it tends to work because learning long temporal relationships is difficult, and here we put the target more proximal to these earlier time steps. So it encourages the model to, even if there's some signal, even if it can't learn it perfectly as of the third time step, it can at least give the best prediction possible given the data that is available through that time step. In this case, we're using a unidirectional model and not a bidirectional model, in part because we imagine we want to be able to run this model in real time. So we want to be able to have a model where we're constantly feeding in new data every single time a new data point becomes available as like actual time is progressing, and we want to be able to keep getting out sort of an up-to-date differential diagnosis of what are the most likely diagnoses given the data that characterize the patient up to the current time. And we explore other things like multitask learning with auxiliary targets. This is another aspect of real learning that'll come up in our finance work, where you say, well, I have multiple features. I have sort of an arbitrary choice about which features to include in my model. One thing that you could do is I can use some things as, or at least features that are, especially for things that are maybe available at training time that wouldn't be available at deployment time, I can use them as auxiliary targets. So I could try to predict the task I care about and also these other tasks. And if they're related, it's sort of well known that there's often a beneficial effect of doing multitask learning, of training simultaneously on all the tasks. So indeed, we got much better performance than multi-layer perceptrons or logistic regressions, even when those models were using sort of expertly handcrafted features. And this gave us some confidence that this was sort of the first paper that anyone had done, to our knowledge at the time, applying modern recurrent neural networks to these complex multivariate clinical time series data, and gave us some confidence that we were sort of on the right path, and that deep learning was sort of more broadly applicable on these kinds of big, messy time series problems and wasn't limited in usefulness to natural language processing. So sooner after we published that paper, around that time, I got a call from John Alberg, who was a tech entrepreneur who built a sort of big enterprise software company and then became an investor and runs a fund called Euclidean. And so we started working together around 2016, shortly after I published that paper. And he was interested in saying, you've got all this technology and you've worked out these tricks for dealing with time series data. Can we apply this on financial data and make predictions that could guide investments? So in this case, it was basically like at the time, now there's many people who know how to train RNNs. At the time, I was one of a few people who knew how to train RNNs, and I guess was public about it or publishing papers and blogging about it, and had worked on data of a similar character. And John had a bunch of clearly related data. So this is work that we published at the NeurIPS time series workshop in 2017, and actually just published a more advanced version of it as an ICML paper this year. So the initial thought was to predict price, and we looked out and said, what features do we want to use? He's a sort of a fundamental fund, we looked at the financial reporting data. So we got things like revenue, cost of goods sold, selling. EBIT, net income, cash and equivalents, receivables, et cetera. And we also included just 4 momentum features to account for any signal that was there in the momentum. Our data was from the CompuStat North America snapshot databases, so this allows us to get views of stocks like that were available at the time, so we could see like the financial record for Q4 as it was known in Q1, not as it was known 3 years later after it was a retrospective accounting correction or something like that. We tried many different versions. We tried discretizing our data to a monthly time step, to an annual time step. So we did a lot of different things. This problem ended up looking quite a lot like the medical time series data. So we dealt with missing values by feeding forward previously observed values, including missing value indicators. We did all kinds of interesting things, like it turned out, originally we thought that the value was in looking at these long time series and being able to handle these varying length time series, but it turned out, at least in our data, we didn't see much value to going back more than 5 years. So it seemed that even if there was more than 5 years of data available, it wasn't actually that useful. So we ended up having something that looked more like a fixed window model. We did interesting things, like one problem that arises, all these values, the dynamic range is huge because you have small stocks and big stocks, right? You have companies that are worth less than $1 billion that are trading, and you have $1 trillion companies that are trading on the same market. And so this factor of 1,000 differences are kind of weird. And so one thing that we did that seemed to be useful is that we would rescale all of our features based on the market cap at the final time step. So when you were looking at a stock, you would look back 5 years. everything in that whole 5-year history would be scaled, all these values based on the final time step market cap, and then you were trying to predict, what would the relative change in market cap be, say, 1 year later. So we did that. We further column-wise scaled the features. We excluded financial sector stocks, and this is just sort of based on my collaborators' sort of belief that they sort of follow different patterns. In those with inflation-adjusted market cap below 100 million, just so that we were sort of, our stocks, universe was not, completely all over the place. And the next question was sort of, what do we predict? So we originally tried to predict price. And the problem here is that this doesn't work out so well. And even when we're able to predict price well in sample, the model seems to perform poorly out of sample. And when I say out of sample, it really means out of domain, because we mean out of the time period in which we were training the data. So we perform well on randomly held out stocks, but we generalize very poorly to the future. And another problem is that we sort of only have one label per time step, and we were looking at the sort of monthly data. We have a limited universe of stocks, so we were kind of prone to some amount of overfitting. So we thought about this, we even when we got a model that was actually generalizing and predicting price well, it wasn't generalizing out of domain. And I hope this sort of motivates sort of what I'll kind of hint at in the rest of the talk, if I don't get to go as deep as I'd like to. So our alternative proposal was to predict fundamentals. And so the idea here was to say, well, what if we don't try to predict price at all? We come up with some kind of heuristic for, like, if you knew price, obviously it's the right thing, right? Because if you knew the future price, you would know exactly what the right trade is now. But it seems that the patterns that we extract when we're trying to fit a model to predict price don't generalize so well out of samples. So what would be a more stable signal? And our alternative proposal is predicting the fundamentals themselves. So the idea is that while price is hard to predict directly, we can instead fit a model to predict the future fundamentals, given the trailing window of the path. So our hypothesis is that fundamentals have a higher signal-to-noise ratio, they're more stable out of sample. And so the idea here is, if someone came back from the future and showed you the quarterly reports from the future, you should be able to make good trades, right? There's a reason why having leaked access to the financial reports should be illegal and is illegal. So our thought is that, if we were able to do this well, presumably, almost all of our intuition says this should be something we could turn into good trades if we were able to do it. The question is just, are we able to do it? And then given that we're able to do it, are we able to do it well enough that we could turn it into trades that are sort of better than random? So we're building on the idea of factor models where, stock prices should in theory indicate cumulative discounted income. We don't know the future income, but and current factor models basically say, well, our best bet of the future, we don't know the future income, so all we can do is look at the current income. Let's look at something like current EBIT divided by enterprise value. So our sort of thought is, well, what if we knew just a little bit into the future? What if we knew not just the current income, but we had a good guess of what it would be 1 year from now? Would we be better off constructing a factor from our current EBIT or based on our 1 year in the future EBIT? And so one way we could test this is through a sort of oracle type experiment. We do a back simulation and we go back and look and say, if we go through time, if we go through, through our window of time of interest, and we say, hey, if all you did was you knew the future income and you constructed a factor where instead of being EBIT divided by enterprise value, it was future EBIT divided by enterprise value. And assuming that God actually told you the exact value of future EBIT, so you have access to an oracle, what would be the sort of simulated, what would be the annualized return that you would get for each of a number of different sort of months of clairvoyance? So like if you saw 3 months into the future and you always traded now based on that, what would be your sort of annualized return, according to the back tester? If you only saw, if you were able to see 12 months into the future, you made decisions now based on the 12 months into the future EBIT, how well would you perform? And interestingly, and specifically for EBIT and net income, not so much for sales and book, which makes sense because this is what it's supposed to be tied to. The further you go out into the future, you get a massive gain in annualized return. So if you could, this shouldn't be surprising that you can make money, but the point is to say that this is sort of confirmation that if you knew the future fundamentals, you could make money from it. And not just that you could make money, you can make a massive amount. Your returns would be much, much, much higher than your returns, using the current factor. So what that sort of tells us, right, it's not surprising, because we should think you should be able to make a lot of money if you had leaked financial reports in the future. But what it really tells us is that, hey, here's a crystal clear, just like specific heuristic to apply, which is like, if you had good forecasts of the future income, this is a way that you could apply it to make trades. This is a way of operationalizing that information. So then what's left to us is to try to figure out, can we make those predictions? How accurately can we make them? So indeed, that's what we do, is we train a model to make predictions of future fundamentals. So indeed, we train a model basically based on these trailing sequences of the fundamental data and train it to predict future fundamentals. So indeed, we do perform over sort of a naive predictor. We certainly don't have zero error, and it's not. We have a magical solution to predicting the future. Some things are unknowable, but the key thing is that our predictor of future fundamentals is significantly better at almost all points in time than the error that we would get if, and this is on average across stocks, it's significantly better than the error that we would get if we just sort of forward filled the current income and predicted that the future income would be the same as the current income, or same as the current income times some, small multiplier that accounts for the typical year-over-year change due to, say, inflation or something like that. So the point is that we don't realize anywhere, if we had realized this perfectly, we'd be getting 40% returns a year, and maybe we wouldn't be talking about it. But the point is that we get a significant but small improvement in predicting the future fundamentals over a naive predictor, and we're able to convert this into a gain in terms of the portfolios that we get. So I don't think I actually have the result slide here, but we end up improving from something like several percent in terms of cumulative annualized return. Again, though, note that so much of what we were doing here is that we're doing the standard thing of fitting a model via empirical risk minimization on the training data, evaluating on the validation data. But then there's a weird part, which is we're then looking sort of, in our case, really based on historical sort of like rolling evaluations, looking at how does that model perform on the future. And remember, with a price model, the problem isn't just that we have trouble predicting the price. The problem is that we have trouble predicting price, not in the validation data, but out of sample. That really falls apart. And that's like the key here, is that ultimately what we're relying on is some kind of folksy intuition here that says, we have practitioners' wisdom that says things like, well, test in the past, evaluate in the future, do this kind of rolling evaluation, keep this out of sample period, roll it across time, see how you would have done historically. But what's missing is actually, we actually have fundamental, deeply understood, if not, guaranteed for all algorithms, principles according to which we expect the generalization from training data to validation data to happen, right? That generalization from training data to holdout data from the same distribution, that's generalization that we somewhat understand. On the other hand, the generalization out of sample here, it's not quite clear why something should work and other things shouldn't work, because what we haven't postulated is what exactly is the sort of structure of the problem that even makes generalization, to a different distribution possible. So I'm going to go through now rather quickly. I normally do a whole talk just on distribution shift, but I want to, sort of go through and just give you a flavor for just how hard a problem this is, why it's so hard a problem, and some, work through even just a very simple example of one kind of assumption you could work with to see how we can make progress, but making progress requires injecting some kind of structural knowledge of the problem. So, the standard setting for machine learning is we just assume that, God showers data out of the sky, that we harvest some of it, use it to train a model, and that in the future, God's going to shower more data out of the sky. We're going to run it through our trained model. And basically, because the sort of transition function between the past and the present, or the present and the future, however you want to think about it, is the identity function. It's just copy paste. Basically, the performance we're going to get on the test, in deployment, is going to be, we can basically estimate it just by taking a random partition of our training data, because there really is no difference between the distribution that generated our training data and that generated our test data. The reality is that all kinds of things happen. In the market, trading strategies change, major financial corrections happen, accounting corrections happen, laws change. Business itself fundamentally changes, the economy changes, all kinds of weird things happen that give you this sort of ambiguous relationship between the past and the present. In the context of medicine, they might start using new MRI machines. The rendering of the images might look slightly different. In the case of image classification on images from the internet, Instagram or Snapchat might introduce a bunch of new filters that become popular, and suddenly this is going to start changing what photographs look like. And you want, your model that was trained on photographs to predict well in the future. So there's all kinds of issues here. So, one of the very popular settings that people analyze is a setting in which the underlying distribution is basically the same, but we say that in the future, there's someone who's allowed to make small changes to each image before you see them. So it's basically composing the original data distribution with some kind of perturbation model. In some work with one of my students, Danish, we showed that basically these vulnerabilities are not limited to image models, but we showed that even on state-of-the-art language classifiers, that by even adding like one adversarial spelling mistake per document was often enough to bring a state-of-the-art classifier down to or below the level of random guessing. So with two attacks, you can do even worse. So I'm going to work through just a simple example to show you how one, to kind of reveal the fundamental problems of thinking about problems of distribution shift, but also to show how when we do have some structural knowledge, we're able to do something coherent and creative that sort of will make the problem sort of addressable again. So this is from work that really got me interested in this topic, and it's a joint collaboration with Yuxiang Wang, who's now a professor at UC Santa Barbara and is one of my favorite researchers in the world, and Alex Smola, who was, I guess, is my boss on the Amazon side, and Yuxiang's PhD advisor at CMU, and who I continue to work with on related problems. So this work, we just started with a simple thought experiment. We said, imagine that you're trying to predict pneumonia. And so you have something like a situation where maybe pneumonia is really rare. And imagine that you have ground truth for patients of ultimately, were they within, some period diagnosed with pneumonia historically, and you had chest x-rays for patients just coming through for like routine chest x-rays, say on their physical exam or something like that. So imagine that you train a pneumonia predictor based on these chest x-rays when pneumonia is really rare, and you train it, it's really rare, you run it on validation data. You find that the model also only predicts that roughly, the same base rate that you had expected, and at least if your model was say post hoc calibrated, it predicts on the validation data that roughly the right percentage of people have pneumonia. You run the classifier in the wild, again it predicts 0.05% of people have pneumonia, and then you find when you run it in the wild. Several months later, that suddenly the classifier is predicting 5% of people have pneumonia, not 0.05%. So the question, the first question, there's sort of two questions that you have, right? One is how many people really have pneumonia, right? Is it really 5%? Do we believe that number? And the reason why we might not believe that number right away is because if the data, if we know the data is not i.i.d. because the distribution of classifier outputs has changed, and the only way that happens is if the distribution of classifier inputs has changed, right? So the change in the input distribution has induced a change in the push forward distribution. But then there's a question of, well, how many people really have pneumonia? And if i.i.d. was violated, why should we trust our classifier at all? How do we even know we're looking at pictures of pneumonia? How do we know we're not just looking at pictures of, apricots or something totally unrelated? How do we know we're actually looking at chest x-rays? So I'm going to skip over the second motivation that I sometimes use just in the interest of time and kind of get to the formal setup for domain adaptation, which is that we have a source distribution, P of x and y, and from this we observe labeled data. But then we have a target distribution. You could think of this as like the data that we've encountered, in some recent window in the present, where we only see the inputs. We don't know the outputs for the present data. But we can look at a large number of unlabeled inputs, and we can notice, for example, if the distribution of inputs is different than they were in training time. And our objective is we want to predict well on the test data, but and the naive thing to do here is we just train on the training data and apply it on the test data. So we want to somehow leverage the fact that we have a bunch of observations of inputs from the target distribution to sort of update our classifier on the fly to do better than that. We want to do it without seeing any labels y from q of y, right? So it's like how do we improve our classifier despite the fact that we don't have any labeled examples from the new period, only unlabeled examples. Or in summary, we want to detect that a shift has occurred, estimate the new label distribution, and correct our classifier on the fly. So an important thing to note here is that this is actually impossible absent assumptions. It's just not possible at all. And the reason why is there's multiple assumptions that we can make about how this training and target data are related. They are both reasonable. They're both compatible with sort of like, in general, plausible stories, maybe not both plausible about pneumonia, but both plausible about some data set. But if we make, depending on which assumption we make, we're going to get a different answer about what is the optimal thing to do at test time. So basically, if we make no assumption, the problem's fundamentally underspecified because there are multiple distributions, multiple pairs of source and target distribution that are compatible with the same observations, that both could have produced the same observations, even that both could have given rise to the same exact joint distribution. Right, so it's not even just a matter of finite sample, even if we had an infinite number of samples. So the assumption that we're going to work with here is the assumption that if the distribution of labels changes, that can happen, and that will induce a change in the joint distribution, but that the distribution of x given y, the class conditional distributions, does not change. So you can think of this as the world in which y causes x. Someone intervenes on y, but they don't intervene on the process by which x assumes its value given y. So if you're familiar with economics, you can think of this as like, the distribution over y has changed, but the structural equation for generating x given y has not. So this corresponds to the anti-causal assumption. This is the anti-causal setting, in which basically the thing we're trying to predict causes our covariates. I think this is a really important thing to just realize because a lot of practitioners sort of are raised on textbooks that describe regression in terms of the causal setting, right? You describe a model where there's some distribution over x, you apply some labeling function, and you get y, like y equals f of x plus eta, where eta is from some noise distribution. That equal sign is actually an assignment operator, right? This is really a structural equation model that's saying that y takes its value given x, right? That x causes y, but that's often not the case. For example, diseases cause symptoms. Symptoms don't cause a disease. And if the amount of disease changes, we don't expect the distribution of symptoms given disease to change, but we do actually expect the probability of disease given symptoms to change. So this is actually opposite to the standard covariate shift assumption in which we assume that P of y given x is invariant. So we're going to work with this label shift assumption, and what we want is a predictor, a consistent estimator of the target label distribution. We don't want its accuracy to depend directly on the input data dimension because dealing with high dimensionality is hard. And so we're going to exploit off-the-shelf black box predictors to reduce dimensionality to something like 1 or the total number of labels you have, depending upon which formulation of the problem. We're going to have a method that's going to get stronger as your classifier gets stronger. And so basically there's three assumptions. We assume that the label shift assumption, which is that the class conditionals aren't changing. We make a little identifiability assumption. It just says that all the classes that we want any hope of recognizing have to have occurred at least with non-zero probability during the source period. Like if you've never seen mules and you've never seen horses, then you can't differentiate which is which because you've never seen either before. So there's a fundamental unidentifiable problem. And we're going to assume that the classifier's confusion matrix is not degenerate. And that's like maybe the least intuitive condition, but it'll become clear soon. So we can look at the confusion matrices for our classifier and see that they're actually identical for the source. They're different for the source and the target distribution, but that this is actually only up to a rescaling of the columns, right? So this is for a fixed classifier. It didn't even have to be a classifier that was actually even trained on our data, but let's just say, for I think the most reasonable way to approach this is that you train a classifier on some portion of the data available from the source distribution, because that's the only data for which you observe labels, but that if all that differentiates, if the label shift assumption holds, then the real underlying confusion matrix of that classifier is going to be the same on the source and target distribution up to a real rescaling of the columns. And the reason why is because each column here corresponds to an actual Y. What is the actual label? Each row corresponds to what is the predicted label, right? So if you condition on the actual label, then you sample X given Y. We know that the probability of X given Y is the same at source, period, and target. And then you're feeding these X's through your classifier. So you're getting the push forward of probability X given Y. And because probability of X given Y is the same and the classifier is the same, this is the same on the source and target periods. Now we can only estimate this matrix, even though it's the same in source and target period. We can only estimate it with the source data, because only the source data do we observe Y, and thus we could break out the columns of the confusion matrix. But with the target distribution data, what we could do is we could average it all. So we could just take all of our data, feed it through the classifier, and just average the classifier output. So you have this quantity on the left, which is the confusion matrix, the column conditional confusion matrix. So like this is conditioned on Y. Each column is conditioned on a different value of Y. And then you have just the mean classifier output on the target distribution, which we can estimate using the samples, the unlabeled samples from our target distribution. And so the punchline here ends up being that this is just a simple linear system. And by solving this linear system, we actually get out a consistent estimator of the label distribution, which is what we cared about. And then further, we can take that and turn it into a way of improving our classifiers. We can both estimate the new label distribution and update our classifier on the fly to make better predictions in the wild. But keep in mind, the key here is we had to know that Y causes X versus that X causes Y, and we needed to assume that the probability distribution of X given Y was invariant over time. So we can show that, to show that this is consistent, it's pretty easy. We just need to show law of large numbers, that our estimate of the confusion matrix approaches its true value, that our estimate of the mean classifier output on target data also approaches its true value, and then also just that as n grows large, that this confusion matrix, if the underlying confusion matrix is invertible, then the empirical confusion matrix will also be invertible. So we get a nice interpretable error bound. This is basically, you see if you take n and m, which are the amount of source and target data respectively, to infinity, this is going to go to 0, which is just stating that our estimator is consistent. And we can use it now to detect shifts in distribution, to estimate the distribution. So here's detecting shift, showing that when there's really no shift, that our type 1 error is controlled, that there's not many false positives, that we get a lot of statistical power when there's a lot of shift. That the power of our detection of distribution shift improves as our classifier improves, that our estimate is indeed consistent, so it's approaching, our errors, our MSE is approaching 0 as n gets larger, and that we're able to use it on the fly to update our classifiers. You see as we go to the right, our classifiers, the relative performance of our approach, which is incorporating the new label distribution estimates into updating the classifier, performs much better than the unweighted model, which is green. I'm sort of at the limit of my time, but I just like to give kind of a whirlwind shot of where we are with this, is that we've also gone further and said that we can sort of generally think of this, at least the first part of this detection, as a pipeline of dimensionality reduction followed by two-sample testing, and explored a whole bunch of different methods in a large-scale empirical study of ways of combining different dimensionality reduction methods with different two-sample testing methods and figuring out what empirically actually tends to be good at detecting certain kinds of shifts. Something interesting is that sometimes methods are able to detect shifts very quickly, very efficiently, even if it's not the kind of shift that's part of the, that the method is specialized for. So our method is specialized in detecting label shift. We're only able to estimate label distributions when the label shift assumption is true, but our detector of distribution shift it still will, it might fire false negatives, but it won't fire false positives, I should say. Or like we can still trust it. It'll only fire false positives at the correct rate. If there is, even if the label shift assumption is violated. And thus we find, surprisingly, that our methods, which are developed under label shift assumption, are also sensitive to all kinds of other shifts. They're able to pick up things like rotations among the images or Gaussian noise or all kinds of things that don't actually change the label distribution. It turns out to be quite effective. And interesting counterexample is adversarial examples, where in terms of adversarial examples, actually the strangest thing seems to work the best, which is that if you just perform 2 sample tests component-wise on the individual underlying pixels, even if you do some very conservative correction, like a Bonferroni correction, doing individual 2 sample tests on the underlying pixels, you still find that adversarial examples are quite easy to, like the presence of adversarial examples is quite easy to detect. Now, it's possible that if someone was an even smarter adversary and knew that you were trying to detect them distributionally using these kinds of 2 sample testing methods, they might update their procedure. We also went on and kind of developed the thoughts about what actually is the right way to operationalize these estimates to update your classifier on the fly. In our first paper, we used importance weighting, but it turns out there's some interesting interplay between the choice to do importance weighting and the choice to use deep learning, especially if you're in the domain like image classification, where the standard practice is to sort of fit the model until it fits the training data perfectly. In these cases, it seems that actually importance weighting, which is sort of the theory of importance weighting, depends on models misspecification, which is sort of why it's not clear that it should be useful in the context of deep learning. Indeed, is not useful in the context of deep learning in that setting where you train to fit your training data perfectly and train for an absurd number of steps. We also have investigated these popular methods called Domain-Adversarial neural networks. We sort of found some deep problems here. Well, this is an approach where basically you have input and source and target data, often under unspecified assumptions of how they're related to each other. So we've already covered how this is a fundamentally impossible problem. But in our work, we looked at these methods. What they do is they take source and target data and they basically try to train a representation learner such that the 2 distributions are unrecognizable. You cannot infer which distribution the data came from based on the learned representation, but that the source data can be classified accurately based on that representation. And so what this is hoping is that you've sort of aligned the source and target data in such a way that elements from the same classes are aligned in representation space, and thus get the correct classification as long as you got classification right in source data. Unfortunately, this alignment is not guaranteed to happen. It seems to rely on kind of vague or mysterious or unstated principles when it does seem to work. And the failure case is actually quite easy to identify. The failure case turns out to be precisely the setting of label shift. So we showed in this paper, it's from ICML 2019 with my student Yifan Wu, that indeed if the label distribution is different between source and target, the only way you can get this kind of can make them look indistinguishable in latent space is actually by misaligning the data. You have to make some of these target distribution positive points look like source distribution negative points in order to make the 2 distributions look aligned. So we came up with a relaxed version of this objective that seems to perform better in practice, and gave a bunch of examples, both with real data and some kind of toy data. I think that really demonstrates the point. Like you see here, in order to align the distributions in panel B, the traditional domain adversarial approach has to sort of split the green points between positive and negative, whereas our method is sort of allows it to work properly. If you see figure 3C. So it's sort of our approach doesn't guarantee that domain adversarial learning will work, but it sort of at least makes it robust to this. It means that it's no longer guaranteed to fail, at least in this particular kind of case of label shift. Finally, just something that we're really excited about the lab and working on a lot is this question about we sort of already shown now how deep learning is great. However, the real world is plagued by distribution shift. We can overcome distribution shift when we can make sort of really simple, strong assumptions about structure in the data. These structural assumptions allow us to perform well in, say, the unsupervised domain adaptation setting. In our case, the assumption was that y causes x, but that the conditional probability of x given y does not change. And the question is, what can we do in more real messy data sets that doesn't require such heroic assumptions? What are the ways, for example, that we can approach, like messy natural language data? And one thing far on the empirical side that we've been exploring is this idea of learning the difference that makes a difference. Learning like what is it that makes a label apply. So you could say arguably this is in the covariate shift setting. But what we want to know is, basically there's a lot of talk about our models are depending on superficial signals, on spurious signals, they're on biased features, but a lot of times these terms aren't really given clarity as to what precisely they mean. And so we kind of take the approach that the causal features, that what it is to depend on these things is sort of not to be relying on what it truly is that makes the label applicable. So sort of intuition, and you see this coming up in a lot of works, including invariant risk minimization or the work of Jonas Peters, this idea that we believe that the causal features, the relationship between the features that cause the label to be applicable and the label, that these are somehow much more stable across domains than say the sort of chance correlated features. So to give an example, if you train a classifier on movie reviews, it comes up that horror is a super positive feature, and romance is a super negative. Horror is a super negative feature, or romance is a super positive feature. Now, these aren't actually what makes the review negative or positive. You could have a very positive review for a horror film. These things happen to be correlated. The thought is that precisely what's wrong here is that you're not depending upon the features that actually cause the label to be applicable. And so our investigation here with my student Divyansh is focused on, are there ways to sort of elicit the kind of signal that we want? It's possible that, whether horror is actually semantically related with positive, sentiment is maybe not even identifiable from the observational data alone, but what sort of data set could we collect that would make it possible to disentangle these things? And so, and this is what I'll end with, is something we're excited about here is we revisited the crowdsourcing setup, where the normal way that you would label, say, movie reviews is you say, here's a review, give me a label. Here's a review, give me a label. And instead what we do is we say, here's a review and here's the label associated with it. And directly below the review is an editable text box pre-populated with that very same review. And to the right is a counterfactual label, and your job is to edit the review so as to make the counterfactual label applicable. So something really exciting that we've seen is that people actually do a very good job at this task. They're pretty creative. They come up with all kinds of interesting ways, both like making an earnest sentence look sarcastic by flipping adjectives, by replacing kind of modifiers, or they don't simply engage in negation. And you can see what you saw here before is that romantic, has, romance, life, works, both, all these words show up as really important features if, say, you train like a TF-IDF classifier and you try to predict which documents on the original data are positive versus negative. However, we now have a new data set where for every original negative review, we have a positive review, which has been modified in some minimal way. And for every original positive review, we have a negative review, right? And so if we analyze the model only on the counterfactually revised data, we actually get the reverse signal. Horror becomes one of the most positive. So bad and worst and boring remain negative features, but horror actually becomes one of the most positive features. And it's because all that those reviews that contained the word horror were initially negative, but in our new data set, they've all become positive. However, the humans, their instructions were basically only to intervene on things that must be changed in order to make the counterfactual label applicable. So by choosing what to intervene upon, the humans have sort of revealed to us which features are actually related or not. And in the new data set, these correlations are all reversed. Now, the final step is to actually combine these data sets together. In the combined data set, we have half the data, horror is predictive of negative review, the other half is predictive of positive. These actually cancel out. And so that when you train on the original and new data together, what you find is a model that you notice doesn't depend on almost any of those words that you thought were sort of the inappropriate words. Interestingly, if you train a model on just the original data, you get really good performance, but very bad performance on the revised data, and vice versa. However, if you train on the two together, you often get models that are almost as good as the best on either. So it sort of says that, hey, there's some small price to be paid for learning the spurious signal, but it's not as high as you might fear. So anyway, I hope, this is sort of a wide-ranging talk, but I hope you get sort of the feeling of what I think is interesting, that, sort of prediction is something that we've sort of figured out how to do really well, and we're continuing to figure out how to do better, and it's sort of that ship is sort of already on its way. But lurking behind it are all these big, deeper, more fundamental questions about, how can we apply these models in the real world in settings that are not exactly just prediction tasks? So how do we enrich the setting to deal with things like the fact that our underlying data distribution is changing over the time, and yet to nevertheless be able to make effective use out of historical training data. So that's sort of what we're working on. This is sort of a few of our recent works that are poking on these issues from various directions. And it was great to speak for you, and thanks for having me.